In this episode, we're going to shift from automation that runs because a human clicked a button to automation that runs because something happened. That something happened could be a new file arriving, a security alert firing, a workload scaling event, or a change being made in a system of record, and the automation reacts by doing work automatically. Notifications, queues, and function as a service, FaaS. Event patterns are three common ways to build that reactive behavior without turning your environment into a chaotic chain of surprises. Beginners often hear event-driven automation and picture instant magic, but the operational reality is that event-driven systems are only reliable when triggers are designed with clear boundaries, clear responsibility, and strong safety controls. If you trigger automation poorly, you can cause infinite loops, duplicate actions, and sudden stampedes of activity that overwhelm dependencies. If you trigger automation well, you get faster response, better consistency, and less manual coordination, especially in busy environments where problems need to be handled quickly. The goal is to understand how these patterns work at a high level so you can use them to increase reliability rather than to create unpredictable behavior. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A notification is the simplest trigger concept because it is basically a signal that something occurred, often sent to interested parties. In automation terms, a notification might be an event message that says a resource changed, an alert occurred, or a job completed. The key characteristic of notifications is that they are about awareness, not necessarily about guaranteed delivery or guaranteed processing. Some notification systems are best effort, meaning they try to deliver the signal but may not guarantee that every signal arrives exactly once. That matters because automation needs clarity about what it should do when signals are missed or duplicated. Beginners often assume that if a notification fires, the automation will run exactly once, but real systems can deliver duplicates, deliver out of order, or occasionally drop signals under stress. That does not mean notifications are unreliable. It means you must design the automation that reacts to notifications to tolerate those realities. In practice, notifications are excellent for initiating work that can be safely repeated and for prompting checks that confirm state before making changes. When used this way, notifications become a low-latency way to wake up automation without requiring perfect event delivery. Queues add a different kind of reliability because they are designed to hold work until it is processed, which changes the operational contract. Instead of simply broadcasting something happened, a queue pattern usually represents here is a unit of work that must be handled, and the system stores that unit until a worker processes it. This matters because it creates back pressure, meaning if your automation is busy, messages wait rather than disappearing. That back pressure is a reliability feature because it prevents overload from instantly becoming loss, but it also creates latency, which means you must be comfortable with work being delayed during spikes. Queues also help with scaling because you can add more workers to process messages faster, and you can throttle workers to prevent stampedes. Beginners sometimes think queues are only for large systems, but they are valuable in small systems too because they create a clean boundary between trigger and execution. Operationally, that boundary gives you control because you can measure how much work is waiting and how quickly it is being processed. When queues are used well, they turn event-driven automation into a manageable pipeline rather than a bursty chain reaction. Function as a service event patterns add a third shape because they emphasize small, event-triggered execution units that start quickly, do a specific job, and then exit. The appeal is that you don't have to manage long-lived servers for your automation logic, and you can scale execution quickly when bursts occur. The operational risk is that FaaS is not a free pass on reliability. It simply moves the reliability questions into trigger design, concurrency control, and state handling. Because FaaS executions can scale rapidly, they can also create rapid load on downstream systems if you don't control concurrency. They can also be invoked multiple times for the same event, or invoked in parallel for related events, which makes idempotency essential. Beginners sometimes write FaaS functions like tiny scripts that assume a clean start and a single run, but event-driven environments rarely provide that guarantee. The safer approach is to treat FaaS functions as workers in a larger system, with clear inputs, clear outputs, and clear behavior when invoked repeatedly. When you do that, you get the speed of event triggers without losing operational predictability. A practical way to compare these patterns is to focus on the question of guarantees, because guarantees influence how you design safety. Notifications often provide weaker guarantees about delivery and ordering, so your automation should treat them as hints and verify state before acting. Queues provide stronger guarantees that work items will be held until processed, but they require you to handle retries and failures in a disciplined way because messages can be processed more than once in certain failure scenarios. FaaS triggers vary, but many event sources and platforms will retry invocations when failures occur, which can cause duplicate execution if the system can't tell whether the work already completed. In all cases, you should assume that duplicates can happen and that out-of-order arrival can happen, because those are normal failure handling behaviors in distributed systems. This is why idempotency and state awareness are not optional for event-driven automation. They are foundational. The operational mindset is that your automation should be safe when repeated and should confirm what needs to be done based on current state, not based solely on the fact that an event fired. When you design with that assumption, the entire trigger system becomes safer. Event-driven automation also raises the risk of feedback loops, which are one of the most common causes of configuration chaos in reactive systems. A feedback loop happens when an automation action triggers an event, which triggers the same automation again, creating a cycle. For example, an automation job might update a configuration record, which triggers a notification, which triggers another automation run that updates the record again. Beginners often create loops accidentally because they treat events as truth and forget that automation itself changes the world and therefore creates new events. The operational fix is to create clear boundaries about which events should trigger which actions and to include loop prevention signals, such as ignoring events that were generated by the automation itself or using a state check to confirm that the desired outcome is not already achieved. Another protective strategy is to design triggers around meaningful state transitions rather than around any change, because not all changes are worth reacting to. The goal is for event-driven automation to respond to relevant conditions, not to every ripple in the environment. When loop prevention is deliberate, you avoid the kind of runaway automation that can turn a small change into a fleet-wide incident. Another key trade-off is how these trigger patterns handle bursts, because real environments produce bursts during incidents and during deployments. Notifications can flood subscribers during a burst, and if your automation reacts directly to every notification, you can overload your own systems and the systems you depend on. Queues can absorb bursts by storing messages and letting workers process them at a controlled pace, which protects dependencies but can delay the final outcome. FaaS can scale rapidly to handle bursts, which can be great for latency, but dangerous if it unleashes too much parallelism on downstream services. Operationally, you should decide whether your priority during a burst is speed or stability, and then configure the trigger pattern accordingly. Often, stability is the priority, because a burst is when systems are already stressed, and adding more stress can turn a minor incident into a major one. This is why back pressure is such a valuable concept. It allows the system to slow itself down instead of breaking. An automation system that can slow down gracefully is more reliable than one that tries to do everything instantly and collapses. Observability becomes even more important in event-driven patterns because the cause and effect chain can be harder to see. In a manual workflow, a human can remember that they started a job, then another job, then a third job. In an event-driven workflow, many things can happen automatically in response to other things, and if you can't trace the chain, you can't troubleshoot it. Notifications need tracking so you can see which events were emitted and which subscribers reacted. Queues need visibility into backlog, processing rate, and failure rate, so you can tell whether work is stuck or merely delayed. FaaS needs clear logs and correlation so you can trace an invocation back to the triggering event and forward to the actions taken. Beginners sometimes treat logging as optional, But in event-driven systems, it is part of correctness because it's how you confirm the system's behavior. Without observability, you can't easily tell whether automation ran, whether it ran twice, or whether it ran and failed silently. Operationally, you want to be able to answer not only did it run, but why did it run? Because triggers are all about causes. When observability is designed in, event-driven automation becomes explainable rather than mysterious. Security also looks different in event-driven automation because triggers can become indirect control channels, and indirect control channels are attractive to attackers. If an attacker can generate events or inject messages, they might be able to cause automation to run in ways you did not intend. That means you must control who can publish events, who can consume them, and what actions are allowed in response. It also means you should validate inputs to automation functions and treat events as untrusted data until proven otherwise. A notification that says resource changed should not be enough to trigger destructive actions without checking current state and authorization. A queued message should not be allowed to request privilege changes unless the system verifies that the request came from an approved source and matches a valid workflow. FaaS functions should operate with least privilege and should avoid using broad credentials that could be misused if the function is triggered unexpectedly. Beginners often focus on making triggers work and forget that triggers are part of the attack surface. Safe event-driven automation treats triggers as security boundaries, not just as convenience features. A practical operational pattern is to use notifications as early signals, queues as work buffers, and FaaS as execution units, but only when the responsibilities are clear. Notifications can alert the system that something needs attention, queues can hold and pace the required work, and FaaS functions can process work items with clear idempotent behavior. This layered design can reduce chaos because it separates something happened from do the work, which makes the system easier to control. It also provides multiple places to apply safeguards, such as filtering which notifications become work items, limiting queue processing rates, and limiting function concurrency. Beginners sometimes connect event sources directly to actions because it's quick, but quick designs often become fragile designs as the environment grows. Separation of concerns is a reliability feature in event-driven automation because it gives you a way to tune behavior without rewriting everything. When responsibilities are separated, you can handle bursts, retries, and failures with more precision. The operational outcome is that the system remains stable even when the number of events increases. As you design event-driven automation, the most important mindset is that triggers are about coordination, not about certainty. The event tells you something might need to happen, and your automation confirms what should happen based on current state, desired state, and policy. That confirmation step is what prevents duplicate actions and what prevents stale events from causing harmful changes. It also makes your system resilient to out-of-order and duplicated events because you rely on state rather than on event uniqueness. When you combine confirmation with idempotent actions, you get safe retries and safe reruns, which are essential for reliability. Beginners sometimes feel like adding confirmation makes automation slower, but it often makes automation faster in practice because it reduces failures and reduces emergency cleanup. Reliable automation is not the automation that runs the fastest. It's the automation that produces the correct outcome consistently under imperfect conditions. Event-driven patterns are powerful, but they must be disciplined to be safe. To close, notifications, queues, and FaaS event patterns are three ways to trigger automation based on events, and each one carries a different operational contract about delivery, pacing, and visibility. Notifications are great for low-latency signaling, but require you to tolerate duplicates and gaps by verifying state before acting. Queues are great for reliable work delivery and back pressure, but require you to design for retries, ordering realities, and backlog management. FaaS is great for rapid, scalable execution, but requires disciplined idempotency, concurrency control, and strong logging so bursts and retries don't become chaos. The safe path is to design triggers with clear boundaries, prevent feedback loops, pace bursts, and treat events as inputs that must be validated before privileged actions occur. When you do that, event-driven automation becomes a way to improve reliability and response speed without creating configuration chaos. It turns something happened into the right thing happened next, which is exactly the operational outcome you want.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.